Our next speaker will be Katherine Fairchild. She is an engineering team lead at MIT Quest for Intelligence, and Katherine designs and builds models and infrastructure that support research in biological and artificial intelligence.
Thank you for the introduction. I am Katherine Fairchild, the Quest Engineering Team Lead, and I'm going to talk to you as quickly as possible because there's a lot of ground to cover about the building the science of intelligence. And first and foremost, as Martin mentioned, if you are at all interested in the things that we are talking about, please, please, please reach out to me. We would love the help, whether that's via a Europe opportunity if you're an undergrad, or if you're thinking about an MEng, we might have some MEng opportunities opening up with us. And we are also hiring for 2 positions, one directly related to BrainScore and one more related to some of the other stuff you're going to see me talking about. So I would like to put that call out, take it seriously. My information is all over the Quest website. The big questions that the Quest engineering team exists to address is luckily available on the website. That's where I got it. MIT Quest addresses 2 fundamental questions. How does human intelligence work in engineering terms? And how can we use our understanding of human intelligence to build smarter machines for the benefit of society? So you might have caught it, but right there in the Quest mission statement, there's engineering right there, and also engineering. So the benefit to the Quest of having an engineering team will hopefully become clear over the next few slides. So we have missions in the Quest. Each one of them exists to address a different facet of intelligence. Some are already well established, some are getting going, and yet others are yet to be defined. We think of the Quest engineering team as sitting sort of in the center of these missions. So the systems and platforms that we're helping to create are in service of the mission's research, but are hopefully accomplishing things that no one mission could accomplish on their own, and certainly no one lab could accomplish on their own. So the engineering team really thinks of itself in terms of integrating across the missions, helping the missions even integrate within themselves if at all possible, and benchmarking. So really taking the systems that are coming out of the missions and trying to use systems like BrainScore, platforms like BrainScore that can actually show us, are these computational models that we're developing actually aligned with what we know about natural intelligence, the brain and behavior data that we're collecting from those systems. So who's the Quest engineering team? That's the core of it at the moment, although like I said, we're hiring, so if you want your picture up here, hopefully it will be. We also, on each project that we take on, we try to embed our collaborators into the Quest engineering team as much as possible. This allows us to build actual tools that the missions really need, as opposed to the traditional engineering format where you might have a client, your project manager is going to go talk to the client, you come up with some requirements, and hopefully in a couple months you go back to the client with something they may or may not like. We have a much tighter development cycle and really close collaboration with our project collaborators in the missions. We also, as we scale and we build more and more projects, these collaborators become increasingly important in order to allow us to continue maintaining the systems that we're building. So when we have a system like BrainScore, we need to be able to, with the 7 individuals you see here, have a long-term plan for development and maintenance. And that really means that we're relying heavily on community support and the people who use these architectures. So Martin talked about BrainScore. The Quest engineering team contributed quite a bit to the development of BrainScore language. We also, for another example of something else that we have built and are maintaining, have the Quest Stimulus library, which is hosted at stimuli.mit.edu. And basically, the Quest Stimulus library is a website. It exists to address a particular problem. And that problem is that researchers spend an enormous amount of time and resources creating their stimuli for experiments, but then there's nowhere really that central database where you can look up and see, hey, is there stimuli already created that I can take and adapt to my purposes, or share your own when you've made it. So in order to address that problem, the Quest Stimulus Library exists. And specifically, this is Quest-oriented and not just brain and cognitive sciences, because we have made some features on the website that mean that the stimuli that is hosted can be designed either just for natural intelligences, but also for artificial agents, meaning, if you include the metadata and the files necessary to be able to run any sort of model, a computational model on the stimuli that you've presented, that means that there's an entire treasure trove online now where you can go and you can find stimuli that you can show to humans, you can show to computational models, and you can then compare their performance and send it to a system like BrainScore that's going to do that benchmarking for you. We've also, to this end, contributed some stimuli ourselves. This is examples of some Quest-generated stimuli that's part of a rather famous cognitive test suite in order to assess different faculties of intelligence in humans and mammals, and actually crows and some other biological organisms. So one is rather famously called the shell game, where you're just guessing, where the ball is under the dishes, and these are equally applicable to, you can show them to human subjects, you can show them to AI subjects, and all of the necessary files are included. So, you've seen BrainScore, you've seen Stimulus Library, and that's essentially the current state of the Quest engineering systems that we haven't just handed off to some other collaborator, that we actually consider to be a central part of our systems. We are building them, maintaining them, plan to do so in the future. So over here you can sort of see the ideal state of the world emerge for us. So we have the Quest Stimulus Library. We also have the ability to start generating some experiments from that stimuli automatically and send it to a behavioral data collection platform called Lookit that we partnered with. And this starts to get to the beginnings of a larger system when you consider it against BrainScore, which is this integrated benchmarking platform. So you've got your stimuli, you've got your neural and behavioral data that you're collecting, and you're sending it to an integrated benchmarking platform. But obviously, we've only got sort of this part and this part. So how do we get the rest of it? Well, let's go through what we're actually trying to do here and why. Why do we want a system that looks like this? So we have this already. We have this virtual stimuli, task, and environment library and some environments to populate it. The idea is that you can then automatically, ideally, send your found stimuli, task environments into your neural and behavioral data collection pipeline. You can also run your models on it. And then you send those results into a platform like BrainScore for benchmarking. Ideally, then you get some score out, and you can see, okay, this is how well aligned my computational models are with the biological, neural, and behavioral data, and that informs my model development, like what iteration I'm going to do on my computational model to bring it more closely in alignment with that data. It's also going to inform your experiment development. So what experiments, what stimuli do I need to design in order to close some of these gaps? So model development, experimental development. And you can see we've got some of the beginnings of this, but we'd really like to get to the rest of it. So to that end, here are our current projects. You guys are getting a little sneak peek of what the Quest engineering team is very actively working on. We have continued work going on BrainScore with the language mission. We are working very actively on infant gaze coding, which I'll get into very quickly with the developing intelligence mission, and robotic spatial modeling. Also, I'll quickly show you some of that with the embodied intelligence mission. How are these getting us there? Well, hopefully you'll see. So the problem we're addressing with infant gaze coding for the developing intelligence mission is a lot of the pre-verbal and early verbal infants they can't tell you what they're seeing or doing in an experiment. So you get a lot of stimuli that's shown to them, and they react, by looking at the stimuli, and you capture their gaze on video via webcam or whatever. And so you're using gaze as a proxy of attention and making your inferences from that. The problem with this is that then you end up with tons and tons of hours of infants looking at the video, a video of infants looking at the screen, and you have to have some poor hapless undergrad go frame by frame and label all of them. So instead, we have worked for the last few years with collaborators both inside and outside of MIT to automate a robust AI system that is equally usable by both technical and non-technical audiences to run over those videos, give you that gaze label, and you can automatically start doing your inferences instead of hiring the hapless undergrads. So the idea is that this can start actually moving data at scale in an automated fashion into the benchmarking platform. Once we start connecting these components, we start removing the barriers to entry to really making all of those benchmarks that Martin was talking about. Robotic spatial modeling. This is another project we're currently working on. Seems disparate, but again, it connects right back into that larger system we're going for. So here's the problem is, how do we compare biological and artificial agents in tasks where embodied intelligence matters? So earlier I was talking about all of the stimuli that you can deploy in simulated environments and run your computational agents on it. But what about when you actually need to move around and pick things up and move things or avoid obstacles? You might be wondering why Stata is up there, or maybe not. If you go to Stata, that is an obstacle course that you can imagine maybe having a human and a robot go through, and you can compare their performance, how they pick their paths to get to a certain goal, how quickly they get there, what mistakes they make. But what if you want to train your robot 1,000,000 times? Or what if it's not feasible for the robot to run all of these different courses in Stata over and over? Or what if, for whatever reason, you just want the simulation and you want your simulated agents and not based in the robotics, the embodied robot, to have to go through it? Well, we've made it easy with our systems for researchers to create 3D environments with just one quick script from basically any real-world location that they've mapped with laser data, and also, very importantly, to employ models therein that are not just the traditional robotics models that would typically be in here, but would also be the PyTorch-based models, the neural networks, biologically plausible models that people like Ela Feet, who's about to get up here and start talking to you about, is currently developing. So these different components, adding these additional features into this pipeline, will allow us to come up with this system where your stimuli can easily automatically generate experiments, and those experiments can feed the data, the resulting data, into the benchmarking platform. And then it is up to people like Ela to do that feedback loop back into the model development and experiment generation. So we're the engineering team, and next is Ela, who will fill in all of the blanks I just left open.